So number one, it says the titration curve shown below best represents the titration of. Well, if you look at this titration, you start with an acidic solution, so you know you've got an acid. If you notice at your equivalence point, your pH is going to be higher than 7, okay? And so therefore, I know that if I'm titrating with a strong base, then the acid that I start with must be weak, since the pH is going to be higher than 7 at your equivalence point. If it were 7, then if I were titrating with sodium hydroxide, for example, then I would have a strong acid. So I can get rid of C and D because sulfuric acid and hydrochloric acid are strong acids. That leaves A and B. Well, phosphoric acid has 3 protons or 3 hydrogen ions that I can get rid of. So its titration curve would look like this with 3 different equivalence points, which tells me this is not going to be phosphoric acid and instead will be hydrofluoric acid, which is a weak acid reacting with a strong base. Okay? In 2, it says at a given temperature, the equilibrium constant is 1 times 10 to the 10th. What is the value of Kp for the reaction below at this temperature? So if you notice, the way that this reaction here is different from this one, I've taken this reaction, I've flipped it, and I've multiplied it by 1/2. So what you do to your equilibrium constant, if you do that, whenever you flip, you raise it to a negative power. And then if I multiply the reaction by 1/2, I'm going to raise my equilibrium constant by 1/2. And so what I would end up doing is take my Kp and I'm going to raise it to the negative 1/2. Okay? 1 to the negative 1/2 is still 1. And so 10 to the 10th raised to the negative 1/2. Remember, when you raise an exponent, you actually end up multiplying the exponents. So it's 10 times negative 1/2, which gives you negative 5. So your answer is B. In 3, it tells you, consider the decomposition of gaseous AB. Which choice is likely to be true of the system in the reverse direction, meaning A plus B produces AB. Okay? Well, the first thing I notice, since I am decreasing the disorder in this reaction by combining 2 reactants together, I know my delta S will be less than 0 because I'm decreasing disorder. So I can get rid of A and C. The other thing that you should notice is that whenever you form bonds, that is an exothermic process because it releases energy. When you form bonds, it's exothermic, it's negative. When you break bonds, it is endothermic or positive. And so since I'm forming bonds here, my delta H, my enthalpy, is going to be negative because it's exothermic, so my delta H will be less than 0. For 4, it says a saturated solution of calcium fluoride has calcium ions with a concentration of X. So I wrote out the dissolution of calcium fluoride. So calcium fluoride breaks apart into calcium ions and fluoride ions. If this is X, then fluoride's going to be 2X. So my KSP is going to be X times 2X, but I've got to square that 2X, so that ends up giving me 4X cubed. Just be careful because a lot of people forget to square this or forget to put 2X. For 5, it says which procedure could be used to change the equilibrium constant for a reaction. Remember, the only thing that can change an equilibrium constant is changing temperature. And so the only one of these options that involves temperature is A. In 6, which experimental result provides evidence for the assertion that not all boron atoms are identical? A talks about a PES, that there are 3 peaks. That just tells me about the electron configuration of boron. That doesn't help. Okay. B says there are 2 peaks in the mass spectrum of a sample of pure boron. What that tells you, remember, if you're talking about the peaks in the mass spectrum, you have identified 2 different isotopes, which does support the assertion that not all boron atoms are identical, since if you have isotopes, they have different numbers of neutrons. So that's an option. Let's look at the other 2. The 4th ionization energy is almost 7 times as large. That doesn't tell you that there are different versions of boron atoms. And D, boron can combine with oxygen to form trioxide. That has nothing to do with the fact that there are at least two different versions of boron. So the fact that boron exists as an isotope helps to support that assertion, and therefore your answer is B. Okay, so here's my problem. Here's my AP problem for this review. So I'm going to go through it. Okay, so the dissolving of silver nitrate, okay, is represented in the equation above. Is delta G for the dissolving of AgNO3 positive, negative, or 0? Well, since silver nitrate is always soluble, what that tells me is that silver nitrate will dissolve without any outside influence. Therefore, the dissolving of silver nitrate is spontaneous, and therefore my delta G is going to be negative. Okay, so just keeping in mind that silver nitrate naturally will dissolve, and therefore, since that is a spontaneous reaction, that your delta G will be negative. In B, it says, is delta S for the dissolving positive, negative, or 0? Well, since you are dissolving, a solid will become ions, therefore increasing the disorder, meaning your delta S is going to be positive. In C, the solubility of AgNO3 increases with increasing temperature. Okay? So what this is saying is when you increase temperature, you shift to the right, which tells me that since solubility increases when I increase temperature, my delta H, or my heat, must be on the reactant side since it's proceeding to the right when I increase temperature. Since my heat is on the reactant side, that tells me that the reaction is endothermic. Okay? In CII, it says, is the answer you gave in part A consistent with your answers in part B and CI? Explain. Well, I'm going to be using the Gibbs free energy equation here. I know my delta H is positive and my delta S is positive. Therefore, yes, my delta G can be negative, but it will only be negative if my temperature is high enough. Because notice delta S is positive, which could make your delta G positive, but we want it to be negative. So as long as your T, your temperature, is large enough, then the fact that delta S is positive will supersede the fact that your delta H is positive. Okay? In DI, it tells you that you're dissolving sodium iodide. Remember, this is the type of problem, the electrolysis problem, that a lot of people struggle with. So remember, if I'm dissolving sodium iodide, I have 3 possible reactants: Na+, I-, and H2O. So if I look at the different half reactions that are provided, I'm going to scroll up here. Okay, water, iodide, and sodium ions can be reactants. So this reaction here and this reaction here, I've got to flip them in order for water to be a reactant. This reaction here, I have to flip it in order for iodide to be a reactant. Here, water is already a reactant, so I can't flip this one. And here, sodium ions are already a reactant, so I can't flip this one, which tells me that these are my 2 options for oxidation because they have to be flipped, and these are my 2 options for reduction. Therefore, if I look at these 2 different options, since when I flip them, both of these will become negative, that tells me that iodide, this reaction here, that will be my oxidation reaction simply because it will be the most positive or the least negative when it is flipped. So this is the oxidation reaction. The reduction, if I can just compare these guys now, because I'm not flipping these 2 reactions because these are my reduction reactions, therefore water is going to be reduced. And so that's my answer there. So I showed iodide being oxidized and water being reduced. In III, it says which reaction takes place at the anode. We automatically know that's oxidation. Quick, easy answer. For IV, all electrolysis reactions have the same sign for delta G. Well, we know that the sign for delta G is going to be positive simply because all electrolysis reactions are non-spontaneous, because they require some sort of outside energy source in order to actually occur. Therefore, since they are non-spontaneous, which is the definition of an electrolysis reaction, the delta G is positive.